Hi, thank you. So I'm Karen Jex, Senior Solutions Architect at Crunchy Data, and it is a huge pleasure to be here at my second PyCon Italia, this time talking to you about how to optimize your database for analytics. And we've already established that some people in the room other than me actually like databases, which is really cool. First of all, I always have to get the confession out of the way. I'm not a developer, I'm sorry. But as you can see from this diagram of my career so far, I do know about databases. I've worked with databases for 25 years now. I was a DBA for about 20 years, and I was once described as quite personable for a DBA, so make of that what you will. And I'm currently a senior solutions architect, but I still only work with databases. So I've worked with loads of developers along the way, and I still work with developers, and I've learned loads from them. I love going to the different talks at the PyCons, and I try to give back some of what I know about databases. Okay, so what am I actually going to talk about today? To try and help answer that question, I'm going to talk about some of the different kinds of workload that you might be running against your database. In all my diagrams, you will notice that I am very much a database person. I've conveniently missed out the whole application layer. So please forgive me for that. This is my vision of the world. We have the database, and we have kind of everything else that goes on outside of it. OK, so you probably have an application, or maybe many applications, that has a back-end database, or databases. And the database is probably constantly being queried, updated, inserted into by your application users. So it could be a traditional payroll or banking app, it could be online commerce, it could be one of all sorts of different applications. And that typical traditional database activity is what we usually hear called OLTP, or online transaction processing, or sometimes your operational database activity. So that kind of workload is characterized by lots of concurrent connections, so lots of concurrent users, and those users will be usually performing short statements, so they'll be doing quick selects, inserts of just a single row, for example, and they'll be doing multiple of those statements per transaction. So that's what we think of when we describe an OLTP workload. Most of this type of application will then gradually build up data over time. And a lot of them don't actually have a strategy for purging old data, but that's a different story. And at some point, the business wants to make money from, or rather glean insights from, this data. And that means you're going to need to run analytics queries. So analytics workload can take many different forms, and it's got lots of different names, so sometimes known as OLAP, online analytical processing, reporting, decision support, DS, business intelligence, BI. And it's basically any activity that serves to answer real-world business questions. So it might be something like, how successful was our last marketing campaign? What's the impact on our CO2 emissions of performing this action compared to this one? Or how much extra coffee do we need to order for PyCon Italia next year? So this OLAP type activity is characterized by much longer, more complex queries. So it will typically be select activity. It won't be updating your database. You'll be potentially joining data from multiple tables and working on large data sets, which means often it's very resource intensive. Once upon a time, we had the OLTP databases, and we had the analytics or OLAP databases, and the two were very much separate. Data would somehow be extracted from the OLTP systems and imported, inserted somehow into the OLAP system. That could be by an overnight batch process, or sometimes even a weekly roll-up of all that data that then got imported. And that does sometimes still happen, and there are some very good reasons for still doing things that way, but often the business doesn't want to wait overnight or until the next week for that data. It wants to get real-time real-time information, real-time value and insights from the OLTP system. So that means often directly querying those systems. So wherever you've got this OLTP plus OLAP in the same database, you'll hear that called either a mixed or a hybrid workload, and that's the kind of thing that we're going to be talking about today. And it's not a new idea. So Gartner came up with the term HTAP, Hybrid Transactional Analytical Programming, back in around 2010. And it's been described in other places as translytical, or I've seen HOAP, Hybrid Operational and Analytical Processing. So what's the problem with this? It's well established in academic circles that this type of workload presents unique performance challenges. So I've seen papers from 2010, 2011, where researchers identified the fact that running mixed workloads can cause performance issues, and then there are ongoing discussions about the best types of benchmarking, et cetera, to look into the performance of this type of workload. But you'll be really pleased to know, I imagine, that I'm not planning an academic discussion. I want to just focus on the actual practicalities of what you can do if you're in this situation where you've got a mixed workload, how you can make sure you've got performance analytic queries and not have an impact on your day-to-day database workload. So just to recap, chances are your database is optimized for your day-to-day OLTP activity. So lots of short selects, inserts, updates, deletes, potentially deletes, run by multiple concurrent users. Once you add analytics activity into the mix, you've now added on some much more complex queries, long-running queries that are resource-intensive and working on big data sets. So that means you can actually end up with inefficient analytics queries and an impact on your existing database activity. Okay, so we've identified the problem that we're trying to solve. Next, we need to set up an environment so that we can test things out, try things out as we go along. I'm using Postgres for this because that's the RDBMS that I work with day to day, the one that I know and love. And also, it's very quick and easy to set up and work with to test things out. And I'm going to be using pgbench, which is a really simple benchmarking tool that's available by default with PostgreSQL. And I'll show you how that works. So first of all, you initialize pgbench. I am very old school. I do everything on the command line. I apologize for that. Actually, no, I don't apologize. I like it. So I've initialized it in a database that I created called PyCon Italia. The -i flag is what does the initialization, and it's creating me some test tables that it's then going to run the transaction against. I've set a scale factor -s of 100, and I've asked it to create foreign keys between the table just so that it looks a bit like an actual application setup. Okay. So this is what it creates for me. It creates me 4 tables. So I've got my pgbench branches, accounts, tellers, and history tables. These numbers of rows here are the initial number of rows that it will create in those tables with a scale factor of 1. So we've got 100 times that number of rows. The pgbench history table will start out with 0 rows at the beginning of each pgbench run. Okay, so that's it set up. We've got the tables created and we've got some data in there. And this is the activity that it runs by default. You can set it to run any script of your choice. You can actually create your own tables if you want to, but for most demo purposes, or if you just want to try out a few little things, the defaults are great. So it repeatedly runs this transaction, which comprises of 5, I think, if I've counted correctly, short statements, which is based loosely on the TCP/B benchmark, if you're familiar with that at all. And it takes random values of AID, TID, BID, and delta for each of the transactions. So when you want to actually simulate some activity on your database, you run pgbench without the -i. So this time I'm telling it to run for minus T60 tells it to run for 60 seconds. The minus C10 is telling it to run with 10 concurrent clients. This is all running on my MacBook, so you know, I don't want to set it up running with too many concurrent connections just in case I fall it over. But in this case, I'm getting 5,000 transactions per second. So the goal here isn't to get the best performance, it's just to run something so I can see different impacts on the things that I do. And then I've mocked up an analytics query to look a little bit like an annual sales report. Now, those of you that actually do analytics will notice that this is an extremely simple query. It's good enough for demo purposes. This would probably be just one building block of a bigger analytics query. But you know, for running on my database on my Mac, absolutely fine. So before testing anything with my analytics query, I let pgbench run for 20 minutes to generate some data in my pgbench history table, and that gave me about 15 million rows. So we're running this, we're still going to call it an analytics query. We're running this analytics query against about 15 million rows in the database. Okay, so let's have a look at the execution plan for this. So I don't know how many people here are familiar with PSQL. It's the PostgreSQL command line tool. If I say explain, oh, I'll wait for it to come back around. If I say explain analyze, and then my statement, the analyze part tells it to actually run the command, and the explain bit tells it to show me the execution plan, tell me what you've actually done to get the results. So you'll get the actual results rather than an estimation. I apologize, I should have left that to stay on for longer. But what you'll see here is that it's doing some, what it calls external merge sorts. So it's doing some activity on disk. It's taking just over 8 seconds to complete. So there are the external merges on disk. And we can see that it's doing a sequential scan on pgbench history. So it's got to read the whole of that table. Just in comparison, the select statement in that pgbench transaction takes approximately a millisecond to run. Okay, so now we've got the environment in place. Let's have a look at some of the different things that you can do to optimize that analytics type activity, but without having too much of an impact, or any impact preferably, on your day-to-day application. This is definitely not going to be an exhaustive list of all the things you can do. It's not a full performance tuning exercise, even of just that one query, but the idea is to give you an idea of the different areas that you can look at so that you can try things out and see how they go. Again, I'm using Postgres. The details here will be specific to Postgres, but the general ideas are relevant for any relational database system. So I mentioned before, your database is hopefully tuned for your day-to-day activity. So hopefully your database configuration parameters have been carefully considered and set accordingly. If not, I highly recommend having a look at them. And that gives me an excuse for a shameless plug. So this is a talk that I did on that exact subject at DjangoCon EU last year. So they're all about how to set your different Postgres configuration parameters. Okay, so some parameters need to be set across the whole of your database instance. Some parameters can be set for individual users or individual sessions. Some can even be set for individual statements. The ones that have to be set across your whole Postgres instance, you're going to have to find some kind of compromise that works for your OLTP activity and your analytics activity. So that part there can be a bit of a challenge. So I'm just going to talk about a few of the parameters, and I'm going to encourage you to go away and read the docs. The Postgres docs, they're actually not that bad. They're, you know, quite descriptive. It has a full list of all the different parameters, what they do, what the default values are, etc. So you could have a look at that. Firstly, your database connections. So the chances are you won't have all that many concurrent analytics query, sessions, but they are going to be resource intensive. So you probably want to keep an eye on them and make sure there aren't too many of them. You've got the max connections parameter in Postgres, but it's for the entire Postgres instance. By default, it's set to 100, and usually you don't want to set it much higher than that. It's a few hundred max in general for a Postgres instance. But on the other hand, that's not going to be all that useful to you potentially for making sure you don't have too much analytics activity going on in your database. So what might be more useful is to put connection pooling in place. You can have a separate, smaller pool of connections for your analytics activity so that you restrict the number of analytics connections that you can have whilst leaving more connections available for your day-to-day application activity. Work mem. This one says how much memory a query operation or a sort operation can use before it spills to disk and creates a temporary table. So we saw in that execution plan before that we had some files created on disk. It was doing some sorts on disk. So work mem is what impacts when that happens. So the higher work mem, the less chance you'll have of actually going onto disk and doing your work on disk. So complex queries that perform lots of different sort operations will usually benefit from a higher value of work mem. Just be aware, if you set that across the whole instance, so it's 4 meg by default, if you set that to 100 meg or more across the whole instance, if you've got 50 users all running a couple of queries that maybe are using, I don't know, 2 or 3 lots of work mem, that's going to quickly build up into gigabytes of memory across your database. So a better way to do that would usually be to set it for individual statements. You can use this parameter here, set log temp files 0. If you do that, you will see in your Postgres logs every time it creates a temp file. So every time it creates one of these files on disk, if you see that happening lots, then it gives you an idea that at least some of your statements need more work mem. And for any parameter or Postgres functionality that I talk about, I've put the link to the documentation in there. And I have got a link to the slides at the end. Okay, so I tested out the analytics query with different values of work mem. So we could see it was 4 meg to start with. I tried it with 100 meg. This, when I do set, that's just setting it for this statement. Okay, so that one, I can see I still had an external merge on disk, and it was still taking just over 8 seconds. Then I set it to a gigabyte just to see what that did. And I can see it's doing it all in memory now. It's doing what it calls a quick sort. But it only took it down to about 6 seconds, which doesn't seem to me like a huge performance increase for the sake of using a whole gigabyte of memory just for that one small query. So obviously that's going to vary from case to case. It's worth testing out for your particular queries what the best value of that parameter is. Statement timeout. So if you're concerned that you're going to have analytics queries that are going to run away, that are going to run for too long and therefore cause performance issues on your database, you could set statement timeout, which will abort any statement that runs for longer than a given amount of time. It's disabled by default, so statements can run for as long as they want to. You can set it for the entire Postgres instance if you want to. But it's probably better to do it for individual sessions or groups of sessions. So, for example, your normal application activity might be allowed to have statements that run for milliseconds or seconds, whereas you might have analytics queries that are allowed to run for many minutes. Okay, so just to demonstrate that, I've tried setting the statement timeout here. So have a look at what it is to start with. It was 0. I set it to 2 seconds. And then I tried rerunning that analytics query just to confirm that that's actually working. And there I can see it cancelled it. So it's cancelled it there, just over 2 seconds. So cancelling statement due to statement timeout. If you want to know when that's happened, you can make sure that logmin error statement is set to the right value. So that will make sure that any statement that's aborted in that way is written to your Postgres logs so that you can keep track of that. So here are the possible values of that parameter. By default, it's set to error, which means that anything error and above will be logged in the Postgres logs. So yeah, whichever value you set it to, it will log that and above. So if you don't want to see anything to do with this, then set it to panic and you won't see these errors logged. Okay. Indexing strategy. You will probably need specific indexes for these analytics queries. The main thing to be aware of is that indexes need to be maintained. It's not, as well as the space that's needed for an index, it impacts the performance of your updates. So that index has to be kept up to date. So you don't want to be adding too many indexes. You want just the ones that are actually really going to help with your queries. A really useful tool can be the indexes on expressions. So you might, for example, in our analytics query, we'll have a look, we've not just selected a column, we've selected an expression based, a value that's based on an expression on that column. So here I've tried out again, creating an expression-based index. So here I've created the index on my PG bench history table, and instead of creating it on the mtime column, I'm creating it on those 2 columns that I've calculated. Okay, so now we can see that it's using that index. It's taken our execution time down to kind of 5.5 seconds, and we've not got any of those disk scans. Don't forget that each of these things that I'm doing is just one thing. You know, you can put multiple of these together to figure out what works best. And we've just got one query that we're looking at. Obviously, in the real world, you're going to have multiple analytics queries, so it's always going to be a balancing act trying to get the right thing for each of those. Okay, the most performant way of doing something is usually to not do it. So we can pre-calculate, pre-sort, pre-aggregate some of that data that's needed in our analytics queries so that we just do it once. We don't have to keep doing that each time we run our analytics queries. One of the ways we can do that is using stored generated columns. So if I use this generated always as, that's effectively setting a default value for a column in my table. But if I specify stored, that's actually going to calculate it. So when I insert into my test table just the values A and B, it's going to not only calculate that at runtime, sorry, it won't calculate it at runtime, it will insert it physically into the table when I do that insert. So I've now got that calculated value in my table. When I run an analytics query looking for A plus B, I don't have to calculate it each time, it's already calculated for me. Obviously, that's going to have an impact on your insert, so you need to balance that out. Okay, so I'm going to leave out some of these demos just to move on. So I did that in the PG bench history table, and it cut my execution time down to 3 seconds. So that was quite cool. Materialized views are another really good way that you can pre-aggregate and pre-sort your data. So a materialized view is a physical copy of the results of a query. So I said before that that analytics query that we're doing could be just one building block in a bigger query. So we can create a materialized view of that query, so that then whenever we want that block in our query, we don't have to go to those base tables and calculate everything. We can just select it directly from that materialized view where it's already been calculated, aggregated, and sorted. And when I did this, it actually took the execution time down to 2 seconds because we're just looking in the pre-calculated materialized view. And then the final thing really is that the best way to avoid impacting your application database is really not to run these analytics queries against your against your application database. So even if you don't have a completely separate analytics system, there might well be options available to you. You've probably already got a high availability solution in place, so you've got one or more standby databases where the database is being replicated to. You could run your queries against that. Disadvantages are that you can't make any changes there. You'd have to still make those changes against the primary database, so you're still having some impact, but at least the actual queries are running against a different database. So those are the advantages and disadvantages that I mentioned there. But you also have logical replication, where you can have a publisher database and a subscriber database. You can send just some objects, just some tables, to a standby, and you can even have multiple publishers sending to a single subscriber, multiple publishers sending off to multiple subscribers. So you can configure your analytics environment the way you want using that. Obviously, you need the space for all of those extra databases if you do that. But the advantage is, oh, and this is just a Postgres 16 thing saying that you can do that from your standby database now. So you have a lot more flexibility. It's more difficult to put in place, but you have flexibility. You can create extra indexes on that standby database. You can create your materialized views there. You can create those calculated columns so that you're not having an impact on your primary application database. And then, I don't have time for this, but this is a kind of fun thing that the folks at Crunchy Data have been working on, which doesn't solve this particular problem, but I think it's really cool. So I've just put a little link in there. So it's running analytics from your Postgres database. So it's just available with the managed service at the moment. So you run it from your Postgres database using Postgres syntax, and it's got a vectorized query engine that will then let you query things in object storage. So it's quite fun. So you can go and give that a try if you want to. So that was the summary. The best way, if you can, is separate analytics databases, but that's not available to everyone. If not, look at your configuration parameters, your indexing strategy, and see what you can do to pre-calculate and pre-aggregate your data. So hopefully that's given you some useful information and enough of a starting point to go away and have a look at the different things that you can do yourself. Thank you very much.
Thank you. We have the space for the timing for only 2 questions. But sorry for you.
Sorry, and I don't want to stand between people and their lunch either.
Yes. One was, what is your experience of database performance on SSD versus, against, imagine, managed cloud database with much lower IOPs but higher concurrency?
So against?
What is your experience of database performance on SSD hard disk, imagine?
Yeah, so I don't know anybody now who's not running their databases on SSD storage.
Okay.
Yeah, precisely because it's cheap enough now that people don't need to worry about that side of things, and it is so much better. Yeah.
Okay, and the last was removing the index to BigDB is a heavy operation. Did you have a situation when you had the index to run some analytics and delete it afterwards?
So that's where you really want to be able to have that, for example, that logically replicated data, because then you can create those indexes without having an impact on your primary database. That's probably the ideal in that case. Yeah.
Thank you.
Thank you very much.